Hi, so you have finished your Thermochem lab. We're now going to tackle the calculations. Remember, what we were doing here was we were having a Q reaction or a Q dissolution, and that was equal to the negative Q of the solution. That's just the first law of thermodynamics. The energy of the universe is constant. The heat of the universe is constant. Therefore, Q reaction is equal to negative Q solution. The Q reaction, of course, is what we're interested in, but this is what we could experimentally observe. So, to get started with our, first, before we do this, Q solution, since this is a solution and we're not changing phase, is equal to mass of the solution, C of the solution, and delta T of the solution. And that is what we're going to be working with all day today. Now remember also that for coffee cup calorimetry, which is constant pressure calorimetry, that the change in enthalpy is equal to Q. All right? So as we find these Q reactions, we're going to be able to find the change in enthalpy of those reactions as well. So now, here's some data I got a few years ago. This will not be yours because obviously things have changed, but this is the data I got. So moles per liter is what molarity is, and that's going to be important to remember. The first thing that we had to do was mass, in trial 1, was mass some solid NaOH on the analytical balance. And the mass that we got was 2.0560, notice 4 decimal places. We ended up putting that mass of NaOH into a coffee cup that already had water in it. Whoops, let's try to get it in the right spot. So initially we massed the cup. In order to find the mass of the solution, we massed the cup. And then we took the final mass when everything was done. Now this final mass included the mass of the NaOH. So the mass of the solution ended up being 101.23. Well, during the time that we put that NaOH in and before we did the final massing, we watched the temperature change and we recorded it. The initial temperature that was recorded was 23.12 degrees Celsius. The final temperature was 28.36 degrees Celsius. So the change in temperature that this particular run got was 5.24 degrees Celsius. So now we took that information and we remembered that Q equals mc delta T, equals mc delta T. And we could use, for the solution, we could use 4.184 joules per gram degree C, because it was a very dilute solution. So if you went ahead and plugged in 4.184, and the mass, which was 101.23 grams, grams cancel, and the temperature change, 5.24 degrees Celsius cancels, we ended up with, in kilojoules, we ended up with 2,219 joules, which is 2.2, using proper sig figs, 2 kilojoules. Now, the next thing that we expected you to know was the delta H, the change in enthalpy for this reaction, not per mole, for this reaction in which we only used 2.0560 grams of NaOH, not a whole mole. So this is an easy one. All we have to do is change the sign. Now the next one, we have to actually figure out how many moles were used to get this, how many moles of NaOH. And what we need to know here is the molar mass of NaOH, which is 40.00 grams per mole. Now, we started with 2.0560 grams times 1 mole over 40.00 grams, and that gave us the moles 0.05, don't worry, I'll move this over in a second, 39 moles of NaOH. So finally, getting the delta H per mole is simply taking our delta H and our moles and dividing them. So negative 2.22 kilojoules divided by 0.05139 moles. And so for this reaction, or for this dissolution of NaOH, we got 43.2 kilojoules per mole. All right, so we're going to try reaction 2. Now in reaction 2, we combine two solutions. So I took my mass on my top loader balance of my coffee cup, and then I added the two solutions to it. 50 milliliters of HCl, just using your graduated cylinder, and 50 milliliters of NaOH were combined for this reaction. So when I added those, I ended up with 100.23 grams. During the time I put these solutions together, you will have noticed that immediately the temperature change happened, and the temperature change for this one, this particular neutralization reaction with aqueous solutions, was 6.76 degrees Celsius. So again, we're going to be using our Q equals mc delta T. So we've got our C, our mass of solution, again we're looking at just the solution, is 100.23 grams, grams cancel, and our temperature change for this neutralization reaction was 6.76 degrees C, with our degrees C canceling out. And we ended up with 2,828 joules, or in kilojoules, 2.828 kilojoules. Now again, next step is easy. We just stick a negative sign out there because the Q reaction is the opposite of the Q solution. And, oh, now that's interesting. Moles of NaOH, I'm not sure how I'm going to find that because I don't have a mass. No, I don't have a mass, but what I do have is a molarity and a volume. So for this particular moles of NaOH, it's going to be 1.000 moles per liter times the 50 milliliters in liters that you used. So we end up with 0.0500 moles. So finally, again, we're going to take our delta H that we got above for that particular reaction, and we're going to divide it by the moles of NaOH we used for that particular reaction. I have one too many sig figs there, but we'll get rid of it. And my result came out to be negative 56.6 kilojoules per mole. So when I was actually reporting these, I should have reported them to 3 sig figs instead of 4. Why is that? Because my temperature change was only 3 sig figs. So 56.6 kilojoules per mole. Remember, although I'm reporting it on the data sheet to 2.83. When I do my calculations to get my delta H per mole, I don't round until the end. Okay, so that was trial number 2. Our final reaction was when we included solid NaOH and liquid HCl. We weren't just dissolving it in water, we were doing a neutralization reaction. So again, masked the coffee cup and masked the coffee cup with solution. So the solution's mass here was 101.46. Found my temperature change, and this was 11.42. Wow, that jumped. So again, we're going to be using the equation Q equals mc delta T. There's our C. The mass for this reaction is 101.46 grams, and the temperature change is 11.42 degrees Celsius. Lots of things cancel, and we ended up with 4,848 joules, which I could use because I had 4 sig figs everywhere. So the heat for this particular neutralization reaction with solid NaOH was 4.848 kilojoules. And the enthalpy change for the dissolution was 4.848 kilojoules negative, right? This was the heat for the solution that we could measure. This is the heat for the system or the reaction. Now the moles of NaOH used, again, we have a mass, so we can go ahead and find our moles of NaOH, 1.9742 grams divided by 40.00 grams per mole, and that was 0.04936. Finally, when we took the delta H for this reaction and divided it by the number of moles of NaOH for this reaction, the delta H per mole came out to be negative 98.21 kilojoules per mole. Awesome. So if you remember your pre-lab, you'll remember that the sum of the first 2 experiments should be equal to the delta H of the target equation, which is the 3rd experiment. So adding up the first 2 experiment delta H's, we get negative 99.8 kilojoules per mole, right? That's negative 43.2 kilojoules per mole plus negative 56.6. All right, so that is Hess's law, adding those up. The accepted value is from the 3rd reaction, which is negative 98.21 kilojoules per mole. And the percentage error, I'm going to do way over here, is accepted minus experimental divided by accepted times 100%. And that was found to be 1.62% error. That's really good. And that was a really good way to support the whole idea of Hess's law being an actual thing. So we got done that, and that was fun. And then we went on to heat of a combination reaction. And in your pre-lab lecture, I did this with strontium. And so we're just going to go ahead and do the experimental data again from a few years ago, and then do the calculations. Magnesium and magnesium oxide was used for this particular experiment. Of course, you may have calcium or calcium oxide, depending on which station you're at. So again, we're dealing with Q, no, can't do it out there. Q reaction is equal to negative Q solution. And the solution is what we can measure. So here we go. Mass of the solution, subtract the two of these, and we get 101.19 grams. Now, the temperature change for this particular reaction, when we took magnesium oxide, massed it, put it in a cup, and added hydrochloric acid, or the other way around, I guess, the temperature change in this case came out to be 8.37 degrees C. Now, the mass that was used of the magnesium oxide was 1.0221 grams. Remember, this had to be around 1 gram for magnesium oxide, more than that for calcium oxide. So finding the moles of the solid, well, we had to find the molar mass of magnesium oxide first, and that is 40.31 grams per mole. So the 1.0221 grams divided by 40.31 grams per mole. Our grams cancel and we end up with moles. And this was 0.02536. Hopefully you're comfortable with all of this sort of fairly simple treatment of the data. Now again, we're finding the Q of solution, which is equal to MC delta T, which in this case is, I'm going to put the C first because I'm lazy so I don't have to keep rewriting it. The mass was 101. Remember, this is of the solution. And the temperature change was 8.37 degrees C. So this number was 3 in kilojoules. I should write it out in joules here. 3544 joules. Here we had to convert it to kilojoules, so 3.54 kilojoules because we only had 3 sig figs in our temperature change. Again, in order to solve for delta H, we just stick a negative in front of it. This is where we're doing the Q reaction. And for the delta H per mole, it's 3.54 kilojoules divided by the moles, which is right here, 0.02536 moles. And this answer was negative 140 with proper significant figures. Now I'm going to slide my sheet back up so we can look at reaction 2, in which case I was just dealing with magnesium. This one was magnesium oxide. The second one was magnesium. Again, masked my cup, put my hydrochloric acid into it, masked it again, and I found that the mass, after I had done the reaction, I found that the mass of solution was 102.56 grams. Holy cow, look at that temperature change. That's enormous. 22.61 degrees C. And in fact, it should be big. When you are doing a displacement reaction with magnesium or calcium and hydrochloric acid, you should have a significant temperature change. It's quite an exothermic reaction. Now, for magnesium, we were only supposed to use around a half a gram, so on the analytical balance it came out to be 0.4972. Now be careful, because now we're using magnesium, whose molar mass is 24.31 grams per mole. Okay, this for magnesium oxide, it was 40.38 grams per mole, but for magnesium, it's 24.31 grams per mole. Be sure you divide by the correct thing. When you divide 0.4972 by 24.31, you end up with 0.02045 moles. All right, down to the Q solution. Here's our C. Our mass is 102.56 grams. The temperature change was that 22.61 degrees C. And the Q for this ended up being 9,702 joules, or 9.702 kilojoules. Can use 4 sig figs because we had 4 in the temperature change. Delta H, once again, which is Q reaction, is negative 9.702 kilojoules, divided by, let's see, I'll put it over here, 9.702 kilojoules divided by the number of moles of magnesium, 0.02045 moles, came out to be negative 474.4 kilojoules per mole. Okay, we're almost done. Now we just have to actually do our Hess's law. So the first thing that I'm going to write is I'm going to take my magnesium reaction, just because I feel like it, plus 2HCl gives me magnesium chloride plus hydrogen gas. And that was this delta H, negative 474.4 kilojoules. The second reaction was the magnesium oxide. I guess it actually was the first reaction, but I wrote it down second here. And its delta H from up there was 140 kilojoules per mole. And then we also used the formation of water from oxygen and hydrogen gas, which we were given. So now we have to figure out our target reaction is magnesium plus a half oxygen yields magnesium oxide. And we're looking for the delta H for this. So now we have to actually do a little bit of Hess's law. So to begin with, I'm going to look at my target reaction, and I'm going to find the equation. In my case, I wrote it down in line 1. The magnesium is on the correct side with the correct coefficient, which is a strong indication that I leave this alone and I do not change my delta H at all. Now I need to find the half oxygen. It's right here in the formation of water, and it's got the correct coefficient on the correct side of the equation, so I leave it alone. Now I'm looking for magnesium oxide, and it's over here. It's the correct coefficient, but it's on the wrong side. So I'm going to multiply that whole equation by -1, which results in our flipping the equation. Now I have MgCl2 plus water yields magnesium oxide plus 2HCl. And what do I do to the heat? I've multiplied it by -1, so that's now 140 kilojoules per mole. Now on your paper, you're just going to cross this one out right here. But we need to be able to see you crossing that out. I'm going to erase it though. Makes it easier for me to add up. So I have the magnesium oxide I want, I have the half oxygen, and I have the magnesium, so I have to make sure everything else cancels. The 2HCl cancel reactants and products. MgCl2 cancels products and reactants. H2 cancels. And water cancels. And I end up only with magnesium, a half oxygen, and magnesium oxide. And that's exactly what I need for the target reaction. So now I'm going to sum all of this up, and when I do, I get -620.5 kilojoules per mole. Now, several pages back, I had the actual delta H reaction for magnesium, and it was -601.6 kilojoules per mole. So again, percent error, -601.6 minus -620.5 divided by -601.6. Remember to take the absolute value of this times 100%. And the percent error for this was 3.14%. Okay, good job. We made it through that. That's some of the toughest calculations we have this semester, but it's good practice for you for the upcoming exam.